You're about to hear a rebroadcast of Where We Live. It was originally recorded on August 23rd, 2019.
This is Where We Live from Connecticut Public Radio. I'm Lucy Nalpathanchel. It's likely you've heard of Squawkzilla. It made headlines this summer when researchers published a study about the discovery of a giant parrot fossil in New Zealand. NPR reported it took nearly a decade after the bones were discovered for it to be correctly identified as belonging to a giant parrot, one that stood 3 feet tall and weighed 15 pounds. Imagine that at your backyard feeder. Coming up, we learn why giant animals tend to be found on islands. Science writer David Quammen will join us. First, giant animal news doesn't stop at Squawkzilla. There is also news about the discovery of a giant penguin fossil, also found in New Zealand. This fossil indicates the penguin was as tall as a human, and researchers say this is the second discovery of a giant penguin fossil, the first found in Antarctica. So what caused some animals to become big? And why have many of them disappeared? To help us understand these questions and more, I want to welcome back to the show Dr. Nick Pyenson. He's a paleontologist at the Smithsonian's National Museum of Natural History and author of Spying on Whales, the Past, Present, and Future of Earth's Most Awesome Creatures. Nick, welcome back to the show.
Hi, Lucy. Happy to be back.
We loved your book the last time we spoke with you. We wanted to revisit part of what you had written about, and that included that whales started out as four-legged creatures on land about the size of dogs. So tell us more about that.
Right. So we think about whales as being these giants of the ocean, and one of the striking things you realize when you look at their evolutionary history, how they came to be, is that they weren't always like that, and they weren't always in the water. So 50 million years ago, when we find fossils of the earliest whales, are whales that had four limbs that were walking around on land for at least part of the time, and were not that large, probably about the size of a large domesticated dog. So that's a very striking difference from the whales we see today, which are much larger, that live in the ocean and rivers full time. They don't have the ability to really survive on land. That dramatic change is something we can only know about from looking at the fossil record. And one of the neat things I always think about, and I tried to highlight in my book, is that the whales alive today are the largest whales that have ever been. And that's kind of a striking thing because we think of giants as somehow something of the past. The world we live in is somehow not as populated with these gigantic creatures. But the fact is, for the whales alive today, they are the largest whales ever, and they are certainly among the largest vertebrates to have ever evolved in the history of life on Earth. And as a scientist, I feel like we can learn so much from looking at whales and asking these questions about what they can teach us about the so-called rules of biology, how big organisms can be, and what are the various positives and negatives for being that large.
When we look back through the time, how quickly did whales evolve to be the size that we find them today?
That's a great question. So you might imagine that as soon as whales returned to the water, and that happened relatively early on in their evolutionary history. So over 50 million years, in the first 10 million years, we find the first fully obligate aquatic whales. So whales that had no ability to survive for any part of their life history on land. That transition from land to sea happened relatively early on in their history, and yet that didn't really spur the origin of really large body sizes until much later. And so we don't find fossil whales the size of blue whales or even humpback whales until very recently in geologic time. So in the last 2 to 3 to 4 million years is where we start to see these very large whales appear. And that's interesting because that is the onset of ice ages on this planet, and that led to very different conditions in climate and especially in the oceans. And with some colleagues, we argued that the changes in the ice ages to how the oceans are structured, specifically with productivity and the kinds of prey that whales eat, led to the right kinds of conditions to promote very large body size in the whales we see today.
Let's talk about some of the advantages of becoming larger, Nick, when we look at the whales that exist today and the fact that they have grown so large through this recent time. Talk about some of the advantages of being giant in the water.
Right. So whenever we move up and down in size in biology, there's a series of trade-offs as far as we can tell. There's advantages and disadvantages. And among the advantages, certainly for being large, from what we can tell from studying the whales today, is that they're much more efficient in terms of how they migrate. You can migrate much longer distances being very large more efficiently. You can also filter feed more efficiently if you're a baleen whale. Being very large helps filter out large gulps of water and strain out the prey. And certainly it also allows you to deter any attacks from predators. Very large blue whales usually don't fall to pods of killer whales because they're simply too large.
But there's also drawbacks. When you are a particular size, are you more at risk for extinction?
Right. There's some perils to being so large. And one of them is that you're kind of at a little bit of an ecological dead end. To be that large means investing a large proportion of your energy into sustaining that large body size. And for blue whales, that means feeding mostly on a very specific type of food, krill. So if you can't find that food and you're a blue whale, you're in trouble. Evolving to these very large body sizes is a bit of an evolutionary experiment that keeps you at a knife edge of peril and also advantages when you're that large. And certainly today in planet Earth in the age of humans, for whales, that very recently has meant a lot of problems if they're very large. Blue whales, for instance, were decimated by a large-scale pelagic whaling a century ago, specifically targeting the very largest of the blue whales because there's so much oil that they had to yield. And what that's left us with is a planet with much fewer blue whales and much smaller ones as well.
I'm also curious about some of the other giant whales that we have today, fin whales, right whales, also seeing the same challenges as blue whales?
Sure. The challenges to being a large whale on planet Earth in the age of the humans is different depending on where these whales live. Mm-hmm. Let's take North Atlantic right whales, which live right off the Atlantic seaboard here in this part of the country. They were the targets of whaling several hundred years ago. Really, for the last millennium, North Atlantic right whales have been the targets of different scales and different kinds of whaling, whether it was Basque whalers nearly 1,000 years ago or more recently in historical time, Yankee whaling. North Atlantic right whales somehow made it through, and then, despite many decades of protection and cessation of whaling since the early 20th century, not just even the laws in the late 20th century, North Atlantic right whales somehow haven't rebounded, certainly not in the way that maybe humpback whales by comparison. And then North Atlantic right whales also feed in the same shipping corridors that we find very large cargo ships and cruise ships. And it's also the same places where there's a lot of fishing going on, specifically crab traps, lobster traps. So right whales are living in, North Atlantic right whales at least, are living in increasingly urbanized oceans. And that leads to a lot of suffering. Specifically, we find a lot of North Atlantic right whales that end up dead, either from blunt trauma from ship strike or entanglement. Those are the two largest causes of right whales. And when we look at the numbers, they're really, really sobering. There's somewhere in the neighborhood of 400 North Atlantic right whales left on the planet. They live right along the eastern seaboard between the United States and Canada. And the real number that you need to pay attention to is the number of reproductively viable females, the cows that are out there. And there's no more than 100 at best estimates. So we're really concerned about North Atlantic right whales. But there are clear solutions that would allow them to survive. And many people have identified those. And hopefully we'll see more action on that front in the future.
Dr. Nick Pineson's joining us from NPR's Washington, D.C. Headquarters. He's a paleontologist at the Smithsonian's National Museum of Natural History and author of Spying on Whales, the Past, Present, and Future of Earth's Most Awesome Creatures. We invited Nick back to the show because we wanted to learn more about why particular species have evolved to become much larger than their ancestors and why that is. Nick, I wanted to just go back to learning more about whales as they evolved. Ways that their bodies had to adapt because they couldn't just immediately go from small to big. And so if you could maybe clarify that a little bit more for us.
Oh, absolutely. And that's part of the fun of being a scientist is trying to unravel these evolutionary problems, events that nobody was around to see, but that we have the evidence for. And the evidence for someone like me who's a paleontologist, that's the evidence from the fossil record that we care about. That most of the time, those are just the bones, and a lot of the time they're incomplete. So we have to be really good about asking the kinds of questions that we can draw an answer out from looking at the fossil record specifically. When we find the earliest whales, they had a body plan more or less like a dog. 4 limbs, weight-bearing limbs, a nostril at the end of their snout, a tail without a fluke. And within about 10 million years, we see a series of changes. We see the nostrils retract to a position about midway down their snout. We see the modification of their forelimbs into more flipper-like propulsion devices. And eventually, we see their hind limbs disappear. If you come to Washington, D.C., you can walk into the Sant Ocean Hall and see a beautiful skeleton of one of these early whales called Basilosaurus. It sounds kind of like a dinosaur name, and that's because people first thought it was a reptile when they found the fossils from it in the 19th century. And the name sticks with it, even though we know it's a whale, an early whale today. But if you walk along that skeleton, it's some 50 feet long, it has tiny, tiny hind limbs. Those are evolutionary relics of that land ancestry that we see in early whales. So we can talk about the sequence of changes that we see in the fossil record that led to the increasing adaptation of early whales to life in the water. And of course, there's a lot of other pieces of evidence we can use. We can look at the DNA and we can look at different kinds of genes turning on or off relative in whales and relative to their nearest relatives, which happen to be even-toed hoofed mammals, pigs, cows, deer, variety of cattle, camel. So there's a lot of evolutionary changes that happened in whales' history, and we're still trying to figure that out.
I'm curious because we have the blue whale that still exists today. Why, when we think about how big it is, has it reached its upper limit, and why hasn't it gotten bigger, Nick?
Oh, that's a great question. So that's another rubric of what promotes very large body size and what limits very large body size. So clearly being a filter feeder helps you get very, very large in the case of these filter feeding whales. Now there's another group of whales that don't filter feed. Those are the toothed whales that use echolocation. And they have also gotten very large too for different reasons, and we can get into those later. But there has to be some limits on how large a blue whale could be. Otherwise, you might imagine we could see 200-foot-long blue whales or 300-foot-long blue whales out there. And that's really the job of people who apply the mathematics of biology for understanding. And we can look at the numbers, the energetics, how much food in and how much energy has been spent to acquire that food. And the way it seems, based on the math, is that the largest a blue whale could be is somewhere in the neighborhood of 110 feet long. Now, there are not very many 110-foot long blue whales out in the oceans today, but there were 100 years ago prior to whaling. And if you look at the whaling record from that time in the 1920s, you do find accounts of 110-foot long blue whales, the longest ever. And so this is an example where the math and the available data actually converge on a similar answer. It seems like blue whales are at the largest they can be for this kind of lifestyle of filter feeding on very small prey.
And could you talk more about when we look at the different types of whales, the baleen whales versus the toothed whales, why they evolved differently, the reasons behind that?
Right. So baleen whales are mainly going after prey in large concentrations that are mostly at the surface, mostly within the sunlight layer of the oceans. And so this prey is, if you're a North Atlantic right whale, it's copepods, these very, very small watermelon seed-sized animals that feed on phytoplankton and occur in very large quantities around this time of year. This is kind of after the peak, but we do see copepods and a variety of other zooplankton that are the primary food for these filter-feeding whales. For toothed whales, they're diving much deeper and eating different kinds of prey. For a sperm whale, for instance. Now, sperm whales today are the largest for any of the sperm whales we've ever seen in their evolutionary history. And it seems like they got large right around the same time that baleen whales did. That's a really interesting signal that tells us something really is probably real about changes in the ocean's productivity in the last few million years, because that's when sperm whales get large. That's when baleen whales are independently getting large. In the case of sperm whales, the largest of the toothed whales, they're pursuing prey down into the ocean depths beyond sunlight, and that's why they use echolocation to hunt. And sperm whales, just so happens, are going after the largest prey item that they can find, giant squid. So in my mind, that's an example of an evolutionary arms race that has happened over the course of millions of years, and we see the result of that today.
Nick Pynson, before we let you go, we mentioned the peril that the right whales face. Again, blue whales still exist around us today. We shouldn't take for granted that they will be around forever. Just wanted some lasting words from you on, some of the things that we should be looking at for the future.
Absolutely. Ropeless traps and ropeless fishing is a known solution that just requires changes in industry. And so those are geopolitical and economic solutions that are in our toolkit. We just need to execute on them. We humans in general. I don't mean to make that sound like that's an easy thing, but we do know the solution in the case for North Atlantic right whales. One known solution too is changing the timing and availability of the shipping lanes so that if right whales are seen, an alert is put out, everybody can know about it from the immediacy of telecommunications, and you can change the space and the timing of these shipping lanes as well to accommodate this species. So if we think that North Atlantic right whales are important, and arguably whales are very ecologically important to the world's oceans, we want oceans with whales in them in the future for a lot of reasons. Then there are steps that we need to take to make sure that happens. And fortunately, in the case of some species, we do know what those solutions are. Now, there's some 80-odd species of whales out there. Many of those species are in much more precarious situations than North Atlantic right whales. Take the vaquita in the Gulf of California. There's maybe only a few individuals left. And they're at threat because of bycatch. It has nothing to do with what they are, but where they live, the accident of their evolutionary history. So there's a variety of perils that face whales in today's oceans, and I'm sanguine that we can find the right solutions to mitigate their survival in the future.
Dr. Nick Pynson, again, is paleontologist at the Smithsonian's National Museum of Natural History, author of Spying on Whales, The Past, Present, and Future of Earth's Most Awesome Creatures. We'll tweet out a link to that past show we did with Nick. It's a great book. We thank you for your time today from NPR's DC studios.
Oh, thanks so much.
This is Where We Live from Connecticut Public Radio. I'm Lucy Nalpathanchel. Coming up, why are islands a place where you see certain species get really large while others evolve to become much smaller? We're going to hear more about that after the break with science writer David Quammen, and you can join us too. Find us on Facebook and Twitter at Where We Live.
You're listening to a rebroadcast of Where We Live. It was originally recorded on August 23rd, 2019.
This is Where We Live from Connecticut Public Radio. I'm Lucy Nalpathanchel. Were you intrigued by the news about fossil finds in New Zealand that indicated penguins and parrots were much bigger than they are today? Turns out a species becoming very large is not uncommon on islands. We wanted to know more about why that is. Joining us now via Skype is David Quammen, a science journalist and author of many books. One of them, Song of the Dodo, Island Biogeography in the Age of Extinction, which explores the phenomenon of island gigantism. He's also the author of many other books, as I mentioned, including most recently The Tangled Tree. David, welcome to our show.
Thank you, Lucy. Good to be with you.
So many of our listeners familiar with the Galapagos Islands off the coast of Ecuador, thinking of the giant tortoises that can be up to 900 pounds. They live over a century. But these giant reptiles, are they not unique to the Galapagos? You can actually find them on lots of other islands around the globe?
You can't find them on lots of other islands, but you can find giant tortoises on some other islands. People tend, if they don't know too much about it, to think of the Galapagos giant tortoises as this phenomenon that's unique to the Galapagos, something strange about those particular islands. But in fact, it's islands generally. Every island fauna is unique, but unique in its own ways. The island of Aldabra, a granitic island in the Indian Ocean, also has giant tortoises. The island of Mauritius, also in the Indian Ocean, famous as the place where the dodo lived and died, also had giant tortoises. So it's a phenomenon that you see around the world on islands. Strange species evolved in unique ways, in particular gigantism and dwarfism. That's among reptiles, but also among birds and mammals when you find them on islands too.
So tell us more about gigantism. First off, so we're talking about reptiles, but why is it that you see certain birds or even rodents getting bigger on islands?
Right. Well, the first thing to understand about islands is that they tend to be impoverished in terms of biological diversity relative to the mainland. There tend to be lesser diversities of predators and of competitors on islands, and that's a complicated phenomenon. But I can explain the basics of why it's true. If you have a patch of landscape, say a patch of jungle of a certain size on the mainland in South America, and say there are 6 jaguars living in that particular area of jungle. Something happens to those 6 jaguars and they die. What occurs next? Well, other jaguars from other parts of the mainland wander in and fill that habitat. Because they have free movement. There are no boundaries. But if you have the same size of a patch of jungle and it happens to be an island surrounded, for instance, by Lake Gatun in the Panama Canal, there's an island called Barrow, Colorado Island in the Panama Canal, and you have 6 jaguars, and those jaguars die, the jaguar is extinct. It's extirpated on that island because no jaguars are going to be able to wander in. So that's a phenomenon that occurs constantly all over the world. Species are more likely to go extinct on islands because their population sizes tend to be lower and because immigration is unlikely to fill the spaces when they become empty.
There's other examples of reptiles, the Komodo dragons being one. I know you've had an experience, you've written in your book about encountering them. Tell us about this particular reptile.
Oh, yeah. Well, the Komodo dragon is a lizard. It's the world's largest lizard. It belongs to the family of monitor lizards, which are mostly things that might be 4 feet, 5 feet, 6 feet long and weigh 20, 30, 40 pounds. And they tend to be aquatic. They're very good swimmers. But on the island of Komodo, this particular group has evolved into a form, Varanus komodoensis, that's a Komodo dragon. And they grow about 10 feet long, weigh about 200 pounds. They're mostly terrestrial now, but they can still swim. And they are predators. So they eat deer that are found on that island. They occasionally attack horses if humans leave horses vulnerable. There's a theory that they may have evolved to feed on pygmy elephants that once lived on those islands. That's actually a theory that Jared Diamond published in the journal Nature 30 years ago or so. So Komodo dragons are amazing, but they're amazing in the way that lots of other island creatures are amazing. There are giant skinks on the island of Mauritius. There's a giant earwig on the island of St. Helena. There are pygmy hippos that once lived on Madagascar. There's a giant flightless bird that went extinct, lived on the island of Madagascar, grew about 8 or 10 feet tall, weighed 1,000 pounds. They called it the elephant bird. You can see skeletons of it in the museum in Antananarivo, Madagascar. the tiniest chameleon in the world lives on Madagascar. So you have these patterns of reptiles getting larger, mammals in some cases getting larger in their island forms, in some cases getting smaller, like the pygmy hippo or the dwarf elephants. And of course, there are theories about why that happens.
So David Quammen, again, who's a science journalist and author, joining us via Skype. Tell us what the scientists have thought about in terms of trying to figure out why there's certain, again, species that get bigger while others are getting smaller, and some of the researchers that have looked into this phenomenon.
Yeah. Well, so there was a fellow named J. Bristol Foster who published a paper back in 1964. It was also in the journal Nature, if I recall correctly. And he was interested in this phenomenon, size change, gigantism, and dwarfism among island creatures. And it mostly has to do, he suspected, with food supply. How much food is available, how easy it is to acquire food, and what the risks are to you as an animal as you acquire food. So he saw from the empirical patterns that small mammals, like rodents, rats, and mice, tend to evolve toward larger sizes on islands. Why is that? Well, I said there are fewer predators on islands. And if you're a small mammal and there are no predators, then you can afford to take in a lot of food if it's available and evolve toward larger sizes. There's also probably fewer mammals on any given island. Some islands have no mammals at all. And so there's reduced competition. So reduced predation, reduced competition gives small mammals the opportunity to get larger. But then large mammals tend to evolve toward smaller forms. Deer, hippos, other large grazing animals. They seem to, unlike rodents, when they're densely populous, they don't slow down their reproduction. They keep reproducing. So those kinds of mammals seem inclined to out-eat their food supplies on islands, and therefore the bigger individuals might be more likely to die. The smaller individuals might be more likely to survive and reproduce successfully, ergo smaller and smaller forms of these mammals.
So you were talking about Foster's island rule, and then there's also researcher Ted Case who built on what Foster had let out.
Yeah, Ted Case was a wonderful ecologist at UC San Diego. He wrote a paper in the 1970s, 1978. He published this that went much deeper and more mathematically into this phenomenon. And he studied mainly reptiles, but he also applied this thinking to mammals and birds. And again, he emphasized that the net amount of energy that can be gained by a single individual in a particular species in a given amount of time is what was likely to determine the size. So again, few predators, few competitors, small mammals may grow larger until perhaps there are some constraints. For instance, if you're a burrowing rodent and you start to evolve toward a larger size, there's a certain point where you can't live in a burrow anymore because you're this big lummoxy animal and your burrows keep collapsing on you. If you're a gecko, for instance, and you have these sticky pads on your feet, little reptile that famously climbs up and down rock walls and climbs up and down hotel room walls in the tropics, geckos. If you evolve toward a giant form, there's a certain point where these adhesive pads on your feet will not allow you to climb a wall. You're not going to see a 16-inch gecko climbing a hotel room wall in any island that I've ever visited. Likewise, if you're a bird, and it's a nice image, though. And it's actually something you see in tropical hotel rooms, especially in sort of wilder places, bungalows and in remote islands. You see geckos climbing up and down the walls. You also see large spiders climbing up and down the walls, and they police the hotel rooms for mosquitoes and other insects and keep you comfortable. But if you see a 16-inch spider or a 16-inch gecko, it might be a little bit harder to get a night's sleep.
We mentioned earlier, the reason we're talking to you and other scientists, researchers on the show is about the discovery of this fossil of a giant flightless parrot in New Zealand. So let's talk more about the birds that evolved on these islands and got really big. Some famous examples being the moas and the dodo.
Right. Moas were giant birds on New Zealand. So this is not the first giant bird that has been discovered on New Zealand. There was also a giant flightless parrot they call the kakapo. As a matter of fact, the kakapo, if I recall correctly, is not a fossil form. It's still living. It's an endangered species on the island of New Zealand, or the two islands, and it's a it's a parrot so large that it has lost the ability to fly. There was also another fossil form of parrot, giant parrot. They sort of whimsically called it Squawkzilla on the island of New Zealand's two islands and the small islands in between. That went extinct about 20 million years ago. The moas went extinct when humans started arriving on islands. The dodo you mentioned was a giant flightless bird related to the pigeons on the island of Mauritius. And it was also surviving when humans arrived. Humans came in, started killing it to eat it. Also, rats came ashore from the European ships that docked in Mauritius. Somehow monkeys got ashore in Mauritius. Monkeys started eating the eggs of these dodos. They laid their eggs on the ground because they couldn't fly up into a tree. So that combination of things drove the dodo famously to extinction at the end of the 17th century. Mm. And that's why my book is titled The Song of the Dodo. Mm-hmm. It's not just about the dodo, but it's about the whole constellation of subjects of evolution and extinction on islands, and evolution and extinction generally, of which the dodo, as the saying goes, is the poster child.
So the trade-off for these birds that got bigger when they couldn't fly, they were easier for humans to hunt when they arrived.
Right. But for the dodo, for the millions of years before humans arrived, there were no humans on Mauritius before European sailing ships came. It was not occupied by any native peoples earlier on. So it was a paradise of tranquility without predators. And so a bird could evolve to large size, lose the capacity to fly, lay its eggs on the ground, and survive just fine for millions of years, which is what the dodo did, getting bigger and bigger. Why did it get bigger? Scientists speculate that because it was a fruit-eating bird. Fruit would come in pulses of abundance. Certain seasons of the year, there would be plenty of fruit, and the dodo and the dodo's ancestors would capitalize on that, pound down as much fruit as they could, because the lean times were coming. Now, a small bird can't add huge reservoirs of fat, but if the bird evolves towards larger forms with a bigger frame, then it can add more fat. So the dodo got to be the size of a large turkey, and when fruit was abundant, it could swallow fruit after fruit, put on weight, store fat, get itself through the lean times, didn't have to fly because there was nothing that it had to escape from on that island until we humans arrived.
We talked about some of the species that have gone extinct. Before we let you go, David, other examples of recent losses on islands because of humans being around, and also the fact that these big animals lose fear of humans or not used to them because they don't have a lot of predators.
Yeah. Oh, there's a whole long list, Lucy, and I talk about a lot of those cases in my book. The Hawaiian Islands, for instance, was extremely diverse in bird forms until, again, humans started arriving. Polynesians started colonizing eastward in their ocean-going canoes, and so Hawaii was settled by humans. And then Europeans discovered it, and we brought in our camp-following animals, and there were a lot of birds, unique bird species, lost to extinction within recent 1,000 years on Hawaii. Also on other islands throughout the southern Pacific, there were giant flightless forms of rail, R-A-I-L. On a number of those, there were giant flightless geese that went extinct apparently when the Polynesian colonizers started to arrive with their appetites and probably with rats in their canoes. The island of Guam contained unique species. And sometime near the end of World War II, an exotic species of snake got onto the island of Guam, probably from the Solomon Islands or New Guinea. It was a tree-climbing, bird-eating snake, and it started preying on the naive tree nesting birds that had no experience with tree-climbing snakes. There were a number of species that were lost on the island of Guam just in recent decades.
Well, David Quammen, I mentioned that you've written many books, Song of the Dodo, Island Biogeography in the Age of Extinction, written a long time ago. We hope that we've piqued listeners' interest to pick that up again, your most recent one being The Tangled Tree. Science journalist and author joining us today via Skype. David Quammen, thanks so much for your time.
You're welcome, Lucy. Very good to talk with you. Glad you're interested in this subject.
This is Where We Live from Connecticut Public Radio. I'm Lucy Nalpathanchel. Up next, we head back to the mainland to explore the reasons why there are more big mammals in places like the African continent and not in North America. You can join us, too. Find us on Facebook and Twitter at Where We Live.
You're listening to a rebroadcast of Where We Live. It was originally recorded on August 23rd, 2019.
This is Where We Live from Connecticut Public Radio. I'm Lucy Nalpathanchel. When the dinosaurs roamed the earth, it was an age of giant reptiles. But today, most of the largest animals on our planet are mammals. Giant mammals or megafauna like hippos or giraffes are found on the African continent, but why haven't more large species survived today, especially here in North America? Joining us by phone to help us answer our questions is Dr. Emily Lindsay, a paleontologist at the La Brea Tar Pits in Los Angeles. Dr. Lindsay, welcome to the show.
Good morning.
Listeners can also join us. Find us on Facebook and Twitter at Where We Live. So when we think about dinosaurs and then when we think about mammals, so when exactly did they start to become giant?
So when the large dinosaurs went extinct, that's all the dinosaurs except the line leading to birds, that opened up this huge amount of ecological niche space about 66 million years ago. So suddenly there were all these ecosystems on the planet that had really large-bodied animals in them for millions and millions of years, and all of those large-bodied animals were gone. And that, along with a cooling climate, allowed for mammals to start to get larger and exploit these newly open habitats.
When we think about some of the giant mammals, tell us about what they were in North America.
So in North America, there's been, over the last 50 plus million years, a whole range of large-bodied mammals, from things that looked sort of like hippos, things with all kinds of crazy horns all over their heads, things with long necks. And there are several lineages of mammals that we know today that we don't necessarily associate with North America that actually evolved in North America, dogs being one of them. North America had a huge diversity of different dog species in it. Horses evolved in North America and then spread out from here around the world and sort of famously ended up being reintroduced to North America just a couple hundred years ago by the Spanish. And then what surprises a lot of people is camels actually evolved in North America. And from here they spread out. They went into South America and became modern llamas. They spread into Eurasia and became the modern camels and dromedaries. But camels are actually a native North American species as well.
I wanted to hear more about, as a paleontologist, what's been found at the La Brea Tar Pits, but I just wanted to bring up, I had no idea about the giant armadillo. What was it called?
We had glyptodons, which were these armadillo relatives that were about the size of Volkswagen Beetles that were very prevalent in North and South America, right up until just about 10 or 15,000 years ago.
That's really interesting. And coincidentally, our producer, Carmen Baskov, had a picture of one of these from a museum. So the glyptodon, make sure you look it up for those of you who hadn't heard about it before. But again, as a paleontologist at the La Brea Tar Pits, States. Tell us about some of the discoveries there in our understanding of the mammals that were preserved and what was here thousands of years ago.
Well, so the La Brea tar pits is one of the best records of the ecosystem that we had here in North America right before most of the large animals went extinct. So when you think of, say, an African savanna environment today and all of the giraffes and zebras and wildebeest and elephants and hippos and rhinos and lions, that's actually a normal ecosystem for basically every continent on Earth for most of the Cenozoic. That's most of the last 50 million years. Every continent used to look a lot like Africa in terms of having a large number of large-bodied animals and specifically mammals on it. And then between about, depending on which continent you're looking at, about 10 and 50,000 years ago, everywhere except mostly Africa, the vast majority of those large animals went extinct. And so the Earth ecosystems that we see today here in North America or in Eurasia, South America, Australia, these are real departures from what the world has looked like for the last several tens of millions of years. So here in North America, for instance, we had horses, we had camels, we had several elephant relatives, mammoths and mastodons. We had giant ground sloths and giant armadillo relatives. We had tapirs. We had giant beavers a few million years ago. We had a huge number of large carnivores as well. Saber-toothed cats, of course, but also something called the American lion, which is one of the biggest cats that ever lived, particular subspecies of jaguars. So it was just a hugely rich and diverse ecosystem here on the North American continent, right up until just around the time of human arrival on this continent, about 10 or 11,000 years ago. Very suddenly, the vast majority, about 3/4 of these large mammal species went extinct.
Now, I understand there's some debate within the science community about, with the arrival of humans, leading to the extinction of these particular species. Does it have more to do with, say, overhunting versus climate? What do scientists know?
Yeah, so this has been one of the biggest questions in paleontology as well as archaeology for more than half a century now, and it's hard to untangle a bit because there were two important things happening at that time. We were coming out of the last ice age, so we were actually going through the last major episode of global climate change that this Earth saw, which, as we know, from today can have really severe impacts on animal populations. And then the other thing that was happening at the same time, and partly because of these climate changes, was that humans were spreading out to continents around the globe, out of Africa and Eurasia and into Australia and the Americas. And so it's been a challenge for scientists to untangle these two factors and figure out what the relative contribution of each was to the disappearance of this large mammal fauna. But probably, at least in many places, it was actually a combination of both.
When we talk about the African continent, why does why the fact that some megafauna still exist there today when we see them mostly wiped out here in North America? Can you talk about some of the reasons why, Emily?
Sure. So this is another big mystery, and there are several ideas about it. One is that Africa may not have experienced as severe climate changes during the end of the last ice age as many of these other continents did. For one thing, Africa has a very wide latitudinal axis, and so there may have been kind of more opportunity for mammals to migrate in response to climate changes to more favorable habitats. Another idea that a lot of people have speculated is because humans evolved in Africa, the large mammal fauna there was actually able to evolve sort of behavioral defenses in order to mitigate the impacts of hunting or learn to sort of stay away from humans. So we know from more recent experiments in natural ecosystems when new predators are introduced into an area, the prey animals there don't have any innate responses if there haven't been any large predators there historically. So anybody who's been to, say, the Galapagos or Antarctica knows that you can just walk into the middle of a bird colony and nothing will run away from you. There's no innate sense of fear on the part of these animals. And in the same way, in areas even where carnivores have been gone for a very short amount of time. So, for instance, when they reintroduced wolves into Isle Royale up in Michigan, the moose populations there didn't have any innate defenses and really were heavily impacted over the first generation or so because they didn't know to run away from the wolves. So there's sort of this idea that, when humans were coming into a continent with what we call a naive prey, a prey that had never seen this type of predator before, there just wasn't that innate fear response of these new predators. And so that may have led to the impact. And then the last idea is that Africa may actually have experienced at least some degree of extinction that just hasn't been recognized yet. Some scientists have found that the number of large animals on the African continent, as impressive as it is to us, is actually less than one would expect from a continent that size, and that there may have been some earlier extinctions, perhaps more coincident with the evolution of modern humans, that we just haven't picked up in the paleontological record yet.
We're almost running out of time. Dr. Emily Lindsay, again, a paleontologist at the La Brea tar pits in Los Angeles. We're talking with you today just several months after this UN report that found that 1 million species are at risk of going extinct in the near future. Knowing what scientists have uncovered from the Ice Age extinction of large mammals, what are some lessons that we can learn moving forward, Emily?
Well, so clearly the intersection of climate change and human activities can be very devastating for animal populations, especially large mammal populations, which may not be as able to respond to perturbations due to their greater energetic and land area requirements and also their slower reproductive periods. But I think perhaps the most important lesson is that in most cases, the biota that we're looking at today, the animals that we're looking at on Earth today, are actually just the last remnant of what used to be here and what is actually sort of the normal state for Earth ecosystems. So when we're thinking about preserving species and the importance of preserving species, we should remember that these are just the last surviving fragments of what used to be a very rich and diverse group of animals on Earth. And so I think that lends a greater sense of urgency to protecting them.
So the fact that some of these large mammals exist today, beyond just being cool to see them, they really play a role in our ecosystems.
They really do. So we know, especially in areas today, say in Africa, where elephants and wildebeest have been excluded, we see not just a similar savanna ecosystem without elephants and wildebeest, but you actually see a whole-scale turnover of the ecosystem. You go from an open savanna habitat to a much more closed, brushy environment when you lose those kind of large trampling and consumption machines that are native to that ecosystem. And this brings along all kinds of changes. You have changes in the fire regime, you have changes in nutrient cycling, you have changes, of course, in the small animals that are inhabiting this area, you have changes in parasite load, you have changes in dung recycling. So there's some of these large animals can have really outsized impacts on ecosystems. So it's not just a matter of losing one species, but in some cases you lose that whole ecosystem function and go into a tipping point into a completely new ecosystem just potentially from the loss of one species.
I want to thank Dr. Emily Lindsay for joining us, a paleontologist at the La Brea Tar Pits in Los Angeles. We'd love to have you back, and we could just focus on the tar pits. A pretty cool place. I'd love to visit sometime. Dr. Lindsay, are you there?
Yes, thank you so much for having me.
We appreciate you joining us, despite the time zone difference. Today's show produced by Carmen Baskoff, and our technical producer is Kyan Wolf. I'm Lucine Alpathanchel. Have a great weekend.